Hey guys, what's up? It's Ricardo here, and today we have a tutorial on bond-line structures and how to determine the number of carbon and hydrogen atoms within these structures. Let's just jump into it. Alright, so the basics of carbon that we need to know in order to sort of work with these problems, we need to remember that carbon can form maximum a total of 4 bonds. Carbon can never form more than 4 bonds because it doesn't have the amount of orbitals required to do this. And so, if you remember your Lewis dot structures, we know that carbon has 4 valence electrons. And if you want to brush up on this, remember your periodic table here with your different groups. So groups 1A have 1 valence, 2A have 2 valence, 3A have 3 valence, 4A have 4 valence, etc., etc., etc. Remember that carbon falls here, and so it's going to have 4 valence electrons. So in order to satisfy the octet rule, carbon's going to need to form another total of 4 bonds. Now we can do this by forming 4 individual bonds, 2 double bonds, a triple bond and a single bond, any combination of you like which reaches the total of an additional 4 electrons in order to satisfy the octet rule. And so now in terms of the basics of these structures and how they work. Now these structures often look a bit like this. We've got a jagged line like so. Now the ends and the corners here all represent carbons. So if we were to draw the carbons out, it would look like so. Now, remember that carbons, in this case, are bonded to hydrogens, and so this one will have 3 hydrogen bonds here. Now I'm just going to depict the hydrogens as lines. I'm not going to write them at the moment. So we've got another 2 here, 2 hydrogens here, 2 here, 2 here, and 3 here. So it's important to remember that in these bond-line structures, the hydrogens aren't depicted, but they're implied. Because if we look here, for example, at this terminal carbon here, it's only bonded to one other carbon. So in order for it to have a total of 4 bonds, it's going to need 3 other bonds. And these, since they're not depicted by anything, are assumed to be bonds to hydrogen. Now this is important, this only works with sort of neutral carbons. When it comes to positively and negatively charged carbons, the rules are a bit different, and we'll cover that in a later video. So, next we've got double bonds. Double bonds are depicted by adding an extra line, for example. Well, that's a bit shocking, we'll redo that one. So basically double bonds are depicted by adding another line. And so this other line, now if we take a look at this carbon, for example, this carbon is said to be bonded to 2 other carbons. And so you might be like, oh, 2 carbons, therefore to get to 4, 4 take 2 is 2 hydrogens. But since that's wrong. Since it's doubly bonded to this carbon, we doubly weight this carbon. And so it's actually bonded 1, 2, 3 times. And so there's only going to be 1 hydrogen implicit in it. The same sort of rules goes to triple bonds. And triple bonds are normally depicted in a linear fashion when they're drawn out, like so. And so we might look at this carbon here, for example. So there's 1, 2, 3, 4 carbons here, since it's depicted in a linear fashion. And so we take a look at this carbon here. And so this carbon has 3 bonds to this carbon and 1 bond to this carbon. So it's already reached its total of 4 bonds. Take a look at the carbon on the end. That's only bonded to one other carbon. So implicit here is that there's 3 hydrogen bonds. Now these bond-line structures often have substituents and functional groups and a whole bunch of other things which I'm sure you'll encounter in later videos. So if we draw out, for example, this structure and we add maybe a line here with a fluorine, and maybe we'll add a functional group here, of a ketone functional group. So just try and draw a bit better. So that's a straight line. That's not bent. All right. So we obviously have the ends and the corners. So we got 1, 2, 3, 4 up here, and then 5 down there. So just remember that even though it's hidden underneath that double bond, it's still there. And then we also have a little methyl group coming off here. So that's a carbon there coming off, which will have 3 hydrogen groups attached to it. Now, it's important to remember that this here is not a carbon. It is actually bonded to another element. Now, in bond-line structures, you don't represent the carbons, but if it's actually bonded to any other element apart from carbon or hydrogen, they're actually drawn in. So as you can see here, we've got an oxygen, a carbon double bonded to an oxygen here. We've got a carbon single bonded to a fluorine. And so any hydrogens bonded to these elements will be drawn in. For example, you might see a H here, and this will become a positive formal charge, but that's covered in later videos. So that's the basic gist of it. Just to recap, you're going to have carbon forming a maximum of 4 bonds, never more. And it can be double bonded, triple bonded, and these are represented by, in triple bonds, a linear fashion. In double bonds, it's an added line like so. And the ends and the corners will represent carbon atoms. In these structures, there can also be substituents. These can be carbon substituents, like this methyl group here. They can be other elements, like a fluorine group here, and they can be sort of functional groups, like this ketone group here, which is just these carbons here with an oxygen double bonded in between them. And if hydrogens are bonded to these other elements, they will be drawn in. So, let's start going through some practice problems. Now, if you want to pause the video to attempt it yourself, I encourage you to do that, and do so now. And we're going to start by going through all the carbon atoms in each of these, and then we'll go through all the hydrogen atoms on each of these carbons. So, let's dive into it. So in this first structure, I can find my mouse, there you go. We have an end here, a corner here, and an end here. So that gives us a total of 3 carbons. Here we have 1, 2, 3, 4, 5. Here we have 1, 2, 3, 4, 5, and we have this methyl substituent which still counts, so 6. Here we have 1, 2, 3. We've got a double bond to 4 and 5, and we also have the methyl substituents, that's still 6. And here we have 1, 2, 3, and this one's double bonded to an oxygen, but there's still only 3. Here we have a ring. Don't let this fool you, just follow through the rules. We've got 1, 2, 3, 4, 5, 6 carbons. Here we got a benzene ring, which looks a bit more daunting, but it's just a series of conjugated double bonds. And so if we go through it, it's only 1, 2, 3, 4, 5, 6. It's exactly the same number of carbons. What differs is the number of hydrogens, but we'll cover that in a second. The structure here, we have 1, 2, 3, 4, 5, 6, and we go over here, 7, 8, 9, 10. We've got a total of 10. We also have carbon double bonded to an oxygen here, and a carbon double bonded to an oxygen here, as well as another carbon. And going on to the next one, we've got 1, 2, 3. Remember, triple bonds are depicted linearly. So 4, 5, 6. We've got 1, 2, 3, 4, 5, and you might start to go 6 here, but no, remember that this is bonded here to a bromine in this case, and so it's not actually a carbon bond, so we only have 1, 2, 3, 4, 5 carbons here. Here we have a benzene derivative with oxygen and hydrogen up here and a methyl group down here. So if we count, we go 1, 2, 3, 4, 5, 6, 7. Awesome. So that's the number of carbons in each of the structures. Now, the hydrogens. Okay, so let's start at the beginning. So this carbon is bonded to one other carbon, so it's going to have 3 hydrogens in order to make the 4 bonds. This carbon is bonded to one carbon here and one carbon here, so it's going to have 2 hydrogens in order to get to 4. This one, same as the first one, it's only bonded to one other, so it's going to need 3. Now speeding things up a bit, we've got 3 here, 2 here, 2 here, 2 here, 3 here. Same thing going again, 3, 2, 2. Now this one, this carbon here has got a bond to this carbon, a bond to this carbon, and a bond to this carbon, so it's only got 1 in order to reach the 4 bonds. And both of these have 3, as they're only bonded to one other carbon, respectively. So in this case, we've got 3 again, 2 again, and oh, here we go, first double bond of the day. And so this carbon here, has got 2 bonds going to this carbon and 1 bond going to this carbon. So that's a total of 3 different bonds. So in order to reach 4, it's only going to need 1 hydrogen. And then we come to this carbon here, and we see, okay, it's got 1 bond here, 1 bond here, so that's 2, and then another 2 here, so it's already got the 4. So there's no hydrogens at all on this carbon. And these ones here have 3 and 3 respectively. And so here we got 3, here we got 2, and okay. Now don't let this fool you, it's basically the same principle. We've got our carbon here, and it's got 2 bonds, but this time to an oxygen. But that doesn't change in terms of the hydrogens on the carbon. So we've got 2 bonds going to this oxygen, we've got 1 bond going to this carbon, so there has to be 1 hydrogen. Now, for the ring, we've got 1 carbon here, which is bonded to 1 here and 1 here, and so it's got 2 hydrogens, and that's going to be the same for all the different carbons. Now with the benzene, we have, as we can see, a carbon here that's got 2 bonds here and 1 bond here. So it's got a total of 3 bonds, which is going to be 1 hydrogen. If we look at this one here, it's got 2 bonds here, 1 bond here, so 1, the same thing going all the way around. Each carbon only has 1 hydrogen. Now, starting from the top, same as the structure up here, it's only got 2. Now, this carbon here, we've got 1 bond here, 1 bond here, and 2 here, so that's none. There's 0 on that carbon. This one's got a carbon there and a carbon there, so it's got 2, same here, same here. Now for this carbon here, we've got a carbon bond here, carbon bond here, carbon bond here, so that's a total of 3 carbon bonds, remaining 1 hydrogen. Here we have 2 hydrogens, 2 hydrogens. This one here's got a total of 4 bonds, so it doesn't need any, and this one's got 3 hydrogens. Alright, now for the triple bond structure. So obviously this one's going to have 3, this one's going to have 2, and now we have this carbon here, which has got a total of 1, 2, 3, 4 bonds, so it has 0. Same with this carbon here, as it's bonded once to this carbon and 3 times to this carbon. So it's got 0 here as well. This one's going to have 1 carbon here and 1 carbon there, so it's bonded to 2. This M1 is bonded to 3. Spinning things up a little bit, we've got 3 here, 2 here, 2 here. This carbon's bonded once to bromine, once to this carbon, once to this carbon for a total of 3 bonds, so remaining 1 hydrogen is needed. And this N1 has 3. Alright, so our final structure, we've got a benzene ring and substituents, just to mix things up a little bit. So we'll start over here on the side. So remember, this one's got 1, this has got 2 bonds here and 1 bond there for a total of 3 bonds, so remaining 1 hydrogen is needed for the 4 total bonds. 1 there, 1 there. Okay, so now we reach this carbon. Now this carbon's got 1 bond to this carbon, 1 bond to this carbon substituent, and 2 bonds to this carbon. So that's a total of 4 bonds, so there's going to be 0 hydrogens on that carbon. This one's got 3, it's only bonded to one of the carbon. This one's got 1, so this one's bonded twice here, 1 here, once there, so a total of 0. And so that's basically it. That's basically a quick sort of overview of how to calculate the number of carbon and hydrogen bonds in bond-line structures. There's a number of carbon and hydrogens rather in bond-line structures. And so, just a quick recap before we end things up. Carbon can form a maximum of 4 bonds, and the bond-line structures only show the actual elements if they're other than carbon or hydrogen, and they only show hydrogen if they're bonded to an element that's not carbon. And so remember that each end and corner is a carbon, and double dashes are double bonds, and they can be bonded to other elements, not just carbon. Triple dashes, triple bonds, and these are generally in a linear fashion with a gap in between either side. And remember that elements other than carbon are depicted in the structure, such as bromine, and oxygen, and in fact in this case you can see the hydrogen bonded to the oxygen because it's not a carbon. But in the rest of the cases the hydrogens are implied, as we just figured out. Well, thank you very much for watching. I hope you enjoyed this quick tutorial on how to determine the number of carbon and hydrogen atoms in a bond-line structure. I hope it was sort of useful. If you want me to cover any other topics, please let me know in the comment section down below. And if you got any feedback on how to make these videos more engaging, more entertaining, send me through a message. Alright, thank you very much guys, and hope you have a nice day. Until next time, happy studying.